We looked at a tutorial where we could eliminate a complex number on the bottom of the fraction by multiplying the top and the bottom of the fraction by the conjugate of the bottom. So one way to approach this question, we could multiply, the conjugate of the bottom here is 2 minus 4i. We could multiply the bottom of the fraction by 2 minus 4i and the top of the fraction by 2 minus 4i. And when we multiply it out, it'll end up with 0 plus something I. Basically, it would end up looking like this. However, that's a bit more long-winded than the method I've chosen to do. I've simply decided to just view this in the same manner as I'd view algebra. I simply have a fraction and I want to get rid of the fractions. In order to get rid of the fraction, I'm going to multiply both sides by the denominator. If I multiply the left-hand side by 2 plus 4i, then the denominator is just simply gone and I'm left with the top of the fraction. On the right-hand side, I'll have 0 plus ki times 2 plus 4i. So I've eliminated the fraction and life is a little bit easier now. At this stage, we've only got one equation and one unknown, so we'll be able to find a value for k. Now, if we multiply out the right-hand side, obviously 0 times the second fraction is just 0. Ki by 2 gives me 2ki. Ki by 4i gives me 4ki squared. Now remember, whenever we're dealing with complex numbers, instead of an I squared, we can sub in minus 1. So this second term actually just becomes minus 4k. And at this stage, we can let the real value on the left equal to the real value on the right, the complex value on the left equal to the complex value on the right. So we actually have two different ways of finding a value for k here. I'll show you both ways because it's very straightforward. First of all, the real value on the left is 4, and that must be equal to the real value on the right, which is minus 4k. I could divide both sides by 4 here, and I get 1 is equal to minus k. And then obviously I don't want a value for minus k, I want a value for plus k, so I'd simply change my signs and k is equal to minus 1. That's if I decided to just deal with the reals. That's obviously my final answer now, but I could do it just as easily for the imaginary values. The imaginary term on the left is minus 2i, the imaginary term on the right is 2ki. I could divide both sides by I, or in other words, I can just ignore the i's. It's just the coefficient of I on the left equals the coefficient of I on the right. I could divide both sides by 2, and I get minus 1 is equal to k. So it doesn't really matter which one you do there, but by virtue of the fact that I've done both of them, at least I've verified and I know that my answer is correct. In part B of this question, we're asked to find the possible answers of the square root of minus 5 plus 12i. Now it's clear from the wording in the question that you need more than one answer, and it should be obvious to you why. Instead of a square root, I can write it as to the power of a half. So root of minus 5 plus 12i is the same as minus 5 plus 12i to the power of a half. If something is to the power of a half, then that means there's two possible answers. So what we need to do here, the way we're going to do this is we're going to take minus 5 plus 12i, we're going to convert it into polar form. And once we have it in polar form, we can generalize our angle and use de Moivre's theorem to get the two possible answers. So I've started off getting it into polar form here. Remember, minus 5 plus 12i, that's in the form a plus bi, that's referred to as rectangular form. To get it in polar form, we need to write it in the form or cos theta plus I sine theta, where or represents the modulus. And that's the easy bit, and I've already worked it out. To work out or the modulus, it's the square root of a squared plus b squared. In this case, my a is minus 5, my b is 12. And when I plug that into my calculator, the modulus works out as 13. It's far more difficult to get the theta, which we refer to as the argument. To work out the argument, I'm going to use this diagram. All I'm doing here is a rough sketch. Essentially, I want to plot the complex number minus 5 plus 12i. So along the real axis, I'm at minus 5, and along the imaginary axis I'm at 12. Again, it's just rough, it doesn't have to be that accurate. So this, let's say this is the location of minus 5 plus 12i. And I'm going to form a right angle triangle. Join the complex number to the origin, and then join the complex number to the horizontal line. So what I've done here is I've formed a right angle triangle. When we're dealing with right angle triangles, I want you to be thinking of junior cert trigonometry, sine, cos and tan, and Pythagoras theorem. What we can do now is we can work out what this angle is. I'm going to refer to it as the angle A. In this case, I know the distance from here to here is 12, or in other words, the opposite to A is 12. and the distance from here to here is simply 5. Notice I'm not saying minus 5 there, I'm talking about the distance, so I ignore the fact that it's a minus and just the distance itself is 5. So I know the opposite is 12 and the adjacent is 5, so that means I can use the tan. From junior cert trigonometry, we know that the tan of an angle in a right angle triangle is the opposite over the opposite over the adjacent. So I can say that tan A equals 12 over 5. To work out a value for A, I can simply get tan inverse. If tan A is 12 over 5, then A is tan inverse of 12 over 5. I'm going to plug this into my calculator and work out what the angle A is. So I plugged it into my calculator and I've worked out that A is 67.38. Now, I'm not actually looking for A. Remember, what we're trying to do here is rewrite this complex number in polar form. So I need or the modulus and theta the argument. The argument is the angle that the complex number makes with the positive sense of the real axis. That means you should here be thinking about what you studied in the unit circle in trigonometry. We start here and we move in this direction. That's the angle we're looking for. That's our theta. Now, obviously, if I started here and went and ended up here, that's 180 degrees. I know that this angle is 67.38 degrees. So essentially, I'm looking for an angle in the second quadrant. To work out this angle, it's simply going to be 180 minus 67.38. And that will give me my theta, the argument, and then I'll be able to get the actual complex number in polar form. And when we plug this into our calculator, we end up with 112.62. Okay, so now I know the modulus is 13 and the argument is 112.62. That allows me to rewrite my complex number. Now, we have to focus on the fact that the power is a fraction, that it's over 2. The implication there is that there's more than one answer. If there's more than one answer, we have to generalize the angle. Just like we did when we were studying trigonometry, when we were studying the unit circle in trigonometry. So the 13 is going to stay the same, and the cost of the angle is going to change. Instead of using 112.62, I have to generalize the angle. To generalize the angle, when we're dealing with degrees, we add 360n, where you can sub in different values for n and get more than one possible answer. And we do the same thing with the second one. The angle will become 112.62 plus 360n. The reason we do that is because the power is a fraction. Whenever if it's like 1 over 3 or 5 over 6 or any type of a fraction like that, if it's not a whole number, you'll always do this step, you'll generalize your angle. Now, the next step, we're going to actually apply de Moivre's theorem. It's really easy to deal with the 13 according to de Moivre's theorem. It's simply going to be 13 to the power of a half, or in other words, the square root of 13. The funny bit happens with the angle. What we do with the angle, so I'll leave the cos as it is, 112.62 plus 360n, instead of getting it to the power of a half, you simply multiply by a half. So you just multiply your angle by a half. Multiplying by a half is the same as simply dividing by 2. So essentially I can just put all of this over 2. This angle multiplied by a half gives me this. And I do the same thing with the other one, plus I times the sine of 112.62 plus 360n over 2. Obviously there, if you're more comfortable, you can divide in 2 into this number and 2 into that, and maybe that'll make it a little bit more simplified. So that, from there to there, I've applied my de Moivre's theorem. Now, I know the denominator here is a 2, so I need 2 different answers. To get my first answer, I'm going to sub in n equals 0. Root 13 by cos of the angle, then root 13 by sine of the angle, and I'll get my first answer in rectangular form. To get my second answer then, I'm going to sub in n equals 1. If I sub in n equals 1, I'll get a different answer. I'll get the second possible solution to the original expression. So if I sub in n equals 0, then the angle simply becomes 112.62 over 2. Root 13 by cos of the angle gives me 2. Root 13 by sine of the angle gives me 3. So my first answer is 2 plus 3i. Now to get the second answer, now I'm going to sub in n equals 1 and see what I'll get. To get my second answer, I sub in n equals 1. If you sub in n equals 1, your angle is 112.62 plus 360 over 2. Root 13 times the cos of the angle is minus 2. Root 13 times the sine of the angle is minus 3. So this gives me my second possible answer for part B. In part C, we're asked to use de Moivre's theorem to work out three possible answers for z if z cubed equals minus 8. Now, when we're looking for more than one answer for z cubed equals minus 8, we're thinking in terms of complex numbers. So you'll notice here that the first thing I did was, instead of writing it down as just minus 8, I wrote it as minus 8 plus 0i. There's to acknowledge that we're talking about complex numbers here, but the original number actually doesn't have an imaginary element. It's just minus 8 plus 0i. If z cubed equals minus 8 plus 0i, and I'm trying to solve for z, I get the cubic root of each side. And I end up with z is equal to minus 8 plus 0i to the power of 1/3. Now the manner in which we solve this is going to be almost identical to the way in which we solve part B, except it's a little bit easier here. Remember, if we're trying to use de Moivre's theorem, we have to have our complex number in polar form, which means I need to have it in the form of or cos theta plus I sine theta. Or is the modulus, in this case the square root of minus 8 squared plus 0 squared, or simply works out as 8. So that's straightforward enough. And it's actually far easier than in part B here to work out your argument. Minus 8 plus 0i is somewhere there. I'm just doing a rough sketch of it. The argument is the angle that the complex number makes with the positive sense of the real axis. I can just look at my diagram and I can clearly see it's 180 degrees. So my or is 8 and my theta is simply 180 degrees. Which means if I want to rewrite minus 8 plus 0i in polar form, it's simply 8 times the cos of 180 plus I times the sine of 180. So that's another way of writing minus 8 plus 0i. And obviously, I'm trying to get that to the power of 1/3. Now, just like last time, our power is a fraction. Because our power is a fraction, I'm going to get more than one answer. The denominator is a 3, so I'm actually getting 3 answers. The pivotal bit here is, because I want more than one answer, I have to generalize my angle. To generalize your angle, exactly the same as we did in part B, we're going to add 360n. So our angle becomes cos 180 plus 360n, and for the other one I'll do the same. Plus I times the sine of 180 plus 360n. We only ever do this when we're trying to get a complex number to the power of a fraction. If the denominator is more than 1, then we need more than one answer. And on the next step, the next line, we're going to apply de Moivre's theorem. So to apply de Moivre's theorem, the 8 is easy to deal with. It's simply 8 to the power of 1/3. 8 to the power of 1/3 is simply 2. And just like in part B, we're going to multiply the angle by the power. Multiplying by 1/3 means we're just going to put it over 3. Or we can actually do this in our head. 180 multiplied by 1/3 is simply 60. 360n multiplied by 1/3 is 120n. Plus I times the sine of 60 plus 120n. And we're going to have that times 2. Now you'll notice this time it's a little bit different from part B in that the denominator is 3, whereas last time it was 2. But this time it means we need to get 3 different answers. So I'm going to sub in n equals 0, that'll give me my first answer. Then I'll sub in n equals 1, that'll give me my second answer. And finally I'll sub in n equals 2 and that'll give me my third answer. If I continued on and subbed in n equals 3, I get the same answer as I got originally. So if I subbed in 50, 51 and 52, I get the same numbers as I get here. Any 3 consecutive numbers, I'll get the same 3 answers. Let's sub in n equals 0 and get our first answer here. Okay, so I fit in my first 2 solutions here. First thing I did was I subbed in n equals 0. If you sub in n equals 0 into your angle, you clearly get 60 plus 0. So it ends up as 2 times cos 60 plus I sine 60. 2 times cos 60 is 1. 2 times sine 60 is root 3. So my first answer is 1 plus root 3i. If you multiply that by itself 3 times, you'll get minus 8. The second one is I sub in n equals 1, in which case I get 60 plus 120 times 1, which works out as 180. So I get 2 times cos 180, and then 2 times sine 180. I end up with minus 2 plus 0i. Now, looking at the original question, you could probably have gotten this one in your head. Minus 2 by minus 2 by minus 2 gives me minus 8. That's the only one we would have been able to find without using complex numbers. Now we're going to sub in n equals 2 and get our third possible answer. So the third and final answer here is we sub in n equals 2 and we'd get 60 plus 120 times 2, so our angle works out as 300. 2 times cos 300 is 1, 2 times sine 300 is minus root 3i. So the third answer is 1 minus root 3i.